Today I'd like to talk with you about recommended systems. This is a class of algorithms used to recommend items to users. If you have an account with Netflix or YouTube, you log in the system and watch a movie or video. And next time when you log in again, it recommends you with movies or videos based on the videos or movies that you previously watched. Similarly, on Amazon, when you log in the system and you buy a product and more other products, each time you log in, it recommends you with products based on the products that you bought before. There are two types of recommended systems, memory-based and model-based. The first approach relies on data stored in the memory. In the second approach, a model is used. We will talk about content-based recommended systems, collaborative filtering recommended systems, and association rule mining. We first talked about content-based recommended systems. In the memory-based approach, we can measure the similarity between items using features, and then later on provide recommendations based on the similarity between items. As an example, we have a data set of items with features such as X, Y, Z, W. There may be many features, for example, with a data set of lone items in which each row is a lone. And there is a column for lone purpose, which after one hot encoding, we may have 4 different columns, such as business, such as education, personal, and others. We can measure the similarity between items using correlation, cosine values. We will see more about similarity measures later. It may be better to train a model for predicting missing ratings. So let's say we have a rating dataset in which each row is a user and each column is an item. Each user may have rated a number of items. However, there are items that they haven't rated. How can we predict those? And from the predicted rating, provide recommendations to the user. Let's denote n users, the number of users, n items, the number of items. The element Rij in the matrix R is equal to 1 if the user j rates item I, and Yij the rating by user j to item I. Here we use the dataset with items on the row and features on the column for training a model. First, let's treat each user rating like a linear regression problem. For user j, we need to learn a parameter vector theta j. And once we have the learned parameters theta j, given hi, which is the item I with all its features, then the predicted rating of user j to item I can be calculated as theta j transpose times xi. Let's look at the numerical example. Let's say we learned a vector of parameters theta 1 for user 1, and it is equal to this. It has elements 0, 10, 0, 0. And given an item, for example, item number 2, the values of the features are 1, 1, 0, 0. Then the predicted rating of user 1 to item 2 is theta 1 transpose times h2, and it is equal to 10. Sometimes features are not always available. In such a case, we need to look for another different approach. Now first, let's form the cost function. Theta j transpose times xi is the predicted rating for item I of user j. We take the difference between the predicted rating and the true rating, and then square it, and then take a sum over all the items that user j has rated, meaning Rij equal to 1. And averaged by the number of items rated by user j. The number 2 here is just simply to make the derivative look better. When we take the derivative of the cost function, this these two would be cancelling the other two. We also add the regularization term. And here we have a sum for all theta k in the parameter vector theta of user j. And n here is the number of features. The parameter vector looks like this. We have theta naught, theta 1, etc. up to theta k. This term regularized thetas for theta from theta 1, theta 2 up to theta k. And we don't regularize theta naught. To make the cost function look cleaner, we remove m for user j from the cost function. Mj here, as you can remember, is the number of items that user j has rated. Now to learn a parameter vector theta j for user j, we need to minimize this cost function. So we do this by keeping updating theta j for user j iteratively. However, we would need to do the same for all the users to learn a parameter vector for each user. So what we do here is that we add a sum for all the users here and there in the cost function, and now we minimize the cost function for all the users. Now let's denote the function that we need to minimize j. This is the objective function. Taking the gradient of the cost function with respect to theta kj. Theta kj is the parameter theta k for user j. Then we have this. Then plug it in the gradient descent. We have the update rule for theta naught for user j and theta k for user j. Note that we don't regularize theta naught, so that's why we don't see the regularization term for theta naught in here, and only see that term for theta k. So after gradient descent converges, we learned a vector of parameters for user j. So then for prediction, we can just use theta j to predict a missing rating on item I for that user. Given the feature vector xi for item I, the predicted rating of user j to item I is simply theta j transpose times the feature vector for that item. Now we talked about collaborative filtering recommended systems using the memory-based approach. In this approach, similarities between users or items are measured, and then recommendations can be provided. The first approach is user-based collaborative filtering, which is based on the similarity between users. And the second is item-based collaborative filtering, which is based on the similarity between items. Talking about similarity measures, we can use correlation between vectors x and y can be users or items. Additionally, we can use cosine values. If the vector values are binary, we can use simple matching and Jacob coefficients. User-based collaborative filtering systems are the earlier among recommended systems. Similarity between users are used to make predictions. Let's look at this rating dataset. What is the similarity between Alice and Tom, John, Bob, and Amanda? Using correlation as the similarity measure, we can get the correlation between Alice and Tom, Alice and John, Alice and Bob, and Alice and Amanda. Here we can see that the correlation between Alice and John is very high. So it is very likely that what Alice likes is also what John likes. And we can recommend what Alice likes to John, and vice versa. Further, we can also predict the missing rating. Typically, the predicted rating of user A to item P is the average rating of user A plus the weighted sum of the rating difference between rating of user B to item P and the average rating of that user. For all user B in the neighborhood of user A. The weight here is the similarity of user B to user A. The more similar user B is to user A, the more influential the rating of B to the item P is to the rating of user A to item P. The next memory-based approach is item-based collaborative filtering. Item-based or item-item collaborative filtering was invented and used by Amazon in 1998. It was published in an academic conference in 2001 and later on won the 2016 Test of Time Award for their paper Item-Based Collaborative Filtering Recommendations Algorithms. This approach uses the similarity between items to make predictions. The predicted rating of user U on item P is the weighted sum of rating of user U on item I. And item I are actually the items that are rated by the user U. If we call all UI the rating of user U on item I, then we could see that the more similar the item I to the item P, the more influential all UI is to prediction of the rating for user U on item P. There may be a very large number of items in a database However, the item-based filtering approach is not scalable. Amazon came up with the preprocessing approach in 2003, which calculates all the pairwise item similarity in advance, and only calculate that for the small neighborhood because only items that users have rated are taken into account. User similarity change often, so this approach is more stable. We need to store n squared pairwise similarities in the memory. However, in PyTest, this is significantly lower because there are items with no coratings. Finally, we talked about the model-based approach. If you can remember, previously in content-based recommendations, we know that features are not always available. We, however, can learn item features xi given parameters theta j. So for item I, we would try to minimize this function. The first part of the function is similar as we can see in the content-based recommendation approach. However, we now minimize this function with respect to xi. And the regularization term now added for xki. K here is the k feature and I is the item I. So the feature vector looks like this. Actually this is x0, x1, x0 is 1 and x1, x2 and etc. xk up to xn. And because we need to do this for all the items, then we need to sum all the items. Here we put the sum for all the items in here and in there. And we minimize the cost function for all the items. So given the parameters theta 1 for user 1, theta 2 for user 2, theta j for user j, etc., we can learn the features x1 for item 1, x2 for item 2, xi for item I, etc. And if we can remember, right, in previously in the content-based recommendations, given the features x1 for item 1, x2 for item 2, etc., xi for item I, we can learn the parameters theta 1 for user 1, theta 2 for user 2, etc., theta j for user j. So here we have two objective functions. The first part of the two functions are actually the same. We can combine the two objective functions into one. So we can learn both the features and the parameters together. And finally, this is the objective function. In this objective function, we have two regularization terms. One is for features and another is for parameters. In the update rule for gradient descent, we have the updates for the features and the updates for the parameters. So once we have learned the features and the parameters, the weighted rating for item I of either j is theta j transpose times hi. We can write the predicted rating as a matrix multiplication of x and theta transpose. In matrix X, we have the feature vector transpose for item I on the rows, and in the matrix theta, we have the parameter vector transpose for either j.